Hello everyone, my name is Christa Zofall and I'm a quantum applications researcher in the IBM quantum team. And today we're going to be talking about quantum machine learning algorithms for state preparation. First of all, why are we interested in looking at this? Well, we do know that certain quantum algorithms can have an advantage compared to their classical counterparts. For example, in data processing. But in order to apply a quantum algorithm to a data processing task, we do need to first load the data into a quantum state. Now, this loading can actually be very difficult. It's not at all easy depending on the data structure that you want to load. In the worst case, this loading even leads to an exponential overhead. And this exponential overhead would then impair any potential advantage. So what we're now trying to look at is, can we use an efficient but approximate method to load our data and still explore quantum algorithms in the context of data processing? So how do we want to approach our approximate but effective data loading? Well, we want to use parameterized quantum circuits and some machine learning techniques. And today we're going to be discussing two algorithms that approach this problem. In particular, we're focusing on the loading of some probability distributions. So let's get started right away. Let's get started right away. Quantum generative adversarial networks are a combination of parameterized quantum circuits together with a Gantt setting, which is a well-known principle from classical machine learning. Now, the idea is that we want to take some data samples and learn the underlying probability distribution and finally have a representation of this probability distribution in our quantum state. The respective publication can be found here. If you want to look for further details, please check it out. Okay, what are we going to be talking about? First of all, we're going to discuss what generative adversarial networks are, where they come from, then how we can translate the respective concepts into the quantum realm. And finally, we're also going to discuss how we can implement them and investigate some numerical examples. Okay, let's take one step back to clarify our problem at hand. We want to load a probability distribution into our quantum computer such that we can then process it. Now, in a real-world application, we usually do not have a functional description of our probability distribution, but instead we only have some data samples. Now, what we would like to do is to generate a quantum state that corresponds to the underlying distribution, which in fact we don't a priori know. So what we have to do in a direct approach is to take the data samples, model the underlying distribution, and then load the distribution into our quantum computer. Now, let's say we have this model. Then we can do this for certain types of distributions efficiently. But in the most generic case, we do have the problem that this can cost us an exponential amount of gates, and thereby would impair any potential advantage and increase and induce an overhead. What we can do now with quantum generative adversarial networks is to take our data, plug it into our algorithm, and what we get out is a quantum state that was implicitly, but approximately, learned on the underlying probability distribution without even having the need that we need to construct an explicit model. And now this approximate technique can help us to avoid this exponential overhead, help us load our data, and explore quantum algorithms. Okay, let's talk about generative adversarial networks. This type of machine learning algorithms was originally invented in the context of image generation and modification. What a GAN usually does is that it takes some data samples, it learns the underlying probability distribution, and then can generate some samples accordingly. So in this example that we see here, the algorithm received a couple of pictures, or more than a couple of pictures of cat faces. It learned the distribution that corresponds to a cat face, and then it was used to generate some artificial pictures of cat faces. So actually, the figures that you see here are no real cats. The images were artificially generated. Now, how does a GAN do that? We basically have a two-player game. We have a generator, which is parametrized, and a discriminator, which is parametrized. In a classical GAN, those are neural networks. Now, the task of the generator is to generate data samples, and the task of the discriminator is to discriminate whether a data sample that it gets comes from the generator or is a training data sample. And in this regard, it would either label a data sample as being real or fake. Now, the GAN training can be defined through different loss functions. We're now going to focus on a loss function type, which has a particular loss function for the discriminator and one for the generator, and the models are then trained in an alternating fashion. Okay, to train the discriminator, we take a batch of M data samples, as you see here in the sum, and plug them into the discriminator, as you see here. And then the discriminator will discriminate them. We do the same with the generator. So we generate M data samples and plug them into the discriminator and have the discriminator classify them. Now, notably, in the classical sense, the generator is not a stochastic network. So in order to generate different outputs, we need a random input, some prior distribution. Okay, now we have our samples. The discriminator classified them as being either real or fake. Now we plug them into our loss function and we maximize the probability that the discriminator labels the training data samples as being real and the generated data samples as being fake. Now, the generator, on the other hand, wants to fool the discriminator. So what we do here is that we take, again, M data samples. In particular, we generate them, making use again of the random prior. We have the discriminator classify the data and plug it into the loss function, and now maximize the probability that the discriminator labels them as being real. So as you can see now, these two players, the discriminator and the generator, they have an opposing objective. They basically want to be better than the other. So this is a very interesting training behavior. Now, how can we translate this concept into the quantum realm, into the setting that we want? What we're doing is that we replace our parametrized generator neural network with a parametrized quantum circuit. As you can see here, we have an input state. We have a parametrized unitary acting on top, our quantum circuit, which is here G theta. And this ends up giving us a quantum state. Here the ket, the g theta again, which depends on the parameters of our circuit. Okay, now we said that our discriminator gets some data samples from the generator and tries to classify them as well as the training data samples. Now, how could we do this? The training data samples are classical, but the output from the generator is actually a quantum state. What we do now is that we take our quantum state, we measure it, and we map the basis state that we measure into the feature space of our training data. Now we again have a classical data point that can be processed by our discriminator network. One more thing to note here is that a quantum measurement is intrinsically stochastic. What this also means is that we do not need an additional randomness prior. This is something that is intrinsic in our system. Okay, now we know how to get our data samples. Let's have a look at the training. As you can see, the loss functions are basically the same. We generate the samples from our quantum network and we simply plug them into the same loss functions that we've seen before, and also the objective stays the same as before. The discriminator wants to correctly differentiate between generated and real data samples, and the generator wants to fool the discriminator and generate good data samples, which are close to the ones from the training data. Okay, good. So now we saw that how we get our classical data samples, how we can train. Good, let's look at the situation after the training. We have a quantum state from our quantum generator. This is also what we want. But what explicitly should it represent? So what you see here is a superposition over the different basis states, Gi, that we could measure. And then the quantum state is also given by this amplitude that is multiplied by the basis states. Now, what we want to learn is that the amplitudes represent the square root of the measurement probabilities for the PDF of our target PDF. Let's look at this in a bit more detail in a picture. Okay, so basically what we want to see is now, if we measure from this quantum state, then we want to see that the measurement probability for basis state 0 is, as you can see here, for basis state 1, as you can see here, and so on and so forth. We will have a closer look at particularly this plot on the right when we look at the benchmarking results, but just to give you an idea of what we actually want to learn in terms of our representation. Okay, good. Let's take again a step back. What did we want to achieve? What did we do? We said we have our data samples, which we plug into our quantum generative adversarial network. And eventually we want to get out a quantum state, a quantum representation for the underlying distribution. And this is now exactly our final state G theta here, which we can then use in some other quantum algorithms to explore quantum algorithms for data processing. Okay, let's look at one more factor of our quantum generator. We said we have an initial state. Now, what actually makes a good initial state? This is a very important and valid question to ask. We investigated different candidates, as you can read in our paper. So we, of course, investigated some random initializations. So does it maybe not matter where we initialize? Can we always get to a good point? Or would it make sense to have a uniform initial distribution? So allocate an equal proportion of probability mass to each basis state. And then we can form our PDF basically from there. Or we go even more particular into our data structure. We can use some mathematical tools to evaluate the first and second momentum of our training data, and then use this to initialize a normal distribution. So we already used some information for our training data. And as you can see from the paper, actually using the normal distribution, so a targeted initialization, can have beneficial effects on the training of this algorithm. Okay, let's have a look at the benchmarking. You see here 3 simple examples. In the top plot, you see a log normal distribution. In the center plot, you see a triangular distribution. And in the lower plot, you see a binomial distribution. So basically what we have here is that we take those distributions, we truncate them, we discretize them, and then we sample from them, and this gives us our training data. This is what we then plug into our QGAN algorithm to train the quantum state. So what do we use now for our quantum generator? We also use a very simple circuit, which you can find in the Qiskit circuit library. It's called the real amplitude circuit. And we choose for this 3 qubits, which is now a very simple example. And those 3 qubits determine actually the grid that we can represent for our discretized probability functions. Now what you see in the left column is actually the target in the light blue and the trained in the dark blue. The trained now corresponds, as we've seen before, to the measurement probability of the different basis states. And as you can see, for all 3 examples, we get relatively good trainings from our quantum circuit. In the right column, you do see the evolution of the loss function for the generator as well as the discriminator. So we do train the models over 2000 time steps. And as you can see here, we have a difference in the generator and the discriminator loss function, which is also due to the fact that we have this 2-player game. So basically they're trying to fight each other all the time. And then after some time, after some learning time, they converge, they balance each other out a bit, and this then helps us to find a good model. Let's have a look at a more realistic example, so to say. So for this example here, we investigated a model where the training data is given by the first 2 principal components of a multivariate constant maturity treasury rate of US government bonds. The generator here is now again a real amplitude circuit, but since we now have those 2 dimensions, those 2 principal components, we now also need more qubits because we need some qubits that represent each dimension. So we have 3 qubits for the first principal component and 3 qubits for the second principal component. Now, in the plot on the right-hand side, you see the evolution of the relative entropy over our training time. The relative entropy is a distance measure for 2 distributions. And the relative entropy measure that we see here tells us how far our trained distribution is from the target distribution. And as you can see here, we get lower and lower over time, and then we also converge and flatten out. The different lines that you see here relate to different circuit depths. So this means that we can make our variational form, our ansatz, longer or shorter. If a circuit is longer, this also means that it has more parameters in them, which can represent some degrees of freedom of your data. But this also means that you need to put more power and more complexity into training, because you need to train more parameters. So it is important to balance off if you need more representative power or whether you want to have a faster learning. So what we see here actually is that if we have a depth 2, then it's quite bumpy and we don't really get to the best possible loss function value. But if we now compare the depth 3 and the depth 6 lines, then what we do see is actually that the depth 3 even achieves a better relative entropy while having a smaller number of parameters to train. Okay, now to sum this up, we've been discussing QGAT as a way to apply efficient loading of approximations to generic probability distributions. The way that we go about is to use a Gantt setting, replace a classical neural network with a parameterized quantum circuit, and then finally we can use this trained quantum circuit for state preparation and explore its further processing with other quantum algorithms. Let's jump right into our second algorithm of the day, namely quantum Boltzmann machines, or more explicitly, variational quantum Boltzmann machines. Again, if you're interested to learn further details, please find the publication that you see here on the left. The idea of this algorithm is to use more structural knowledge about your data. So, for example, you have some expert that already has an intuition about the data, or you use some preliminary statistical benchmarking. Then quantum Boltzmann machines help you to define a suitable problem in terms of the underlying energy function, the underlying Hamiltonian. And then the way to implement this here is that we are approximating the underlying Gibbs state with a constant depth parameterized quantum circuit. If you don't know what a Gibbs state is, don't worry, we'll talk about that in a bit. Okay, as an outlook again, we're going to discuss Boltzmann machines as well as the quantum counterpart and how we can actually realize them and show some numerical examples. Okay, Boltzmann machines are energy-based machine learning models. So the network that you see here are basically a Boltzmann machine. They can have two types of nodes, hidden nodes and visible nodes. The hidden nodes act as latent variables which kind of encode information in the background. The visible nodes are those nodes which determine the output of our model. In the classical Boltzmann machines, those nodes can be related to a binary state. So they're closely related usually to spin variables. We can see them as being either in the state +1 or -1. Now we can relate this network to an energy function, where the energy function directly reflects the connectivity of our network. So if we have a connection between two nodes, then we do see a respective weighted term in the energy function. And the same is correct for a weighted term for every single node. Now, what we do is that we borrow a concept from thermodynamics. In fact, Boltzmann distributions. A Boltzmann distribution helps us to relate a probability for certain configurations depending on the corresponding energy. So to translate this to our context, we can find the probability for a particular configuration of visible nodes with respect to the configuration's energy and a so-called partition function, the normalization factor, which you see down below, which is a sum over all possible energy configurations and necessary to ensure that we still have probabilities, in fact. Okay, so the goal of this whole Boltzmann machine setting is that we want to train the parameters in the energy function such that the resulting probabilities represent a probability distribution that is again given by some training data and/or labels depending on the learning task. Now, the loss function that we look at here is a cross-entropy loss function, which takes the logarithm of the probability from our model, multiplies it over the probability that we have from the training data, and then averages over all instances that we could possibly see. Okay, let's replace bits with qubits. As you can see here now, we don't have any more nodes, which are either -1 or +1, but now our nodes are given by those sigmas. Those sigmas represent Pauli operators, which can be either the identity X, Y, or Z. And those Paulis are acting then either on hidden, respectively visible qubits. Now the model output is in fact given by the basis, by the configuration of the visible qubits, which are being acted on by our visible Paulis and influenced by our hidden Paulis. Instead of an explicit energy function, we are now defining a Hamiltonian, which is directly related to the connectivity of our network. So as we can see again, if two nodes are connected, then we have a respective weighted term, and the same applies for a weighted term for every single node in the network. Now, the probability to measure a certain configuration of our visible qubits is given as a projective measurement onto our quantum Gibbs state, which is given in terms of the Hamiltonian and again our normalization factor, the partition function. This quantum Gibbs state is now a density matrix which encodes all the sampling probabilities and even more information. Now the normalization factor is something that we should mention that is often difficult to evaluate for some Hamiltonians with a classical computer because of what is called the sign problem. It's not important right now what this is, it's just important here to mention that this is a computation that can be difficult for a classical system. Okay, now we already said that basically our probability distribution is encoded into the Gibbs state. So the Gibbs state is the key component of this algorithm, and we're going to talk about how we can represent an approximation to the state with a parametrized quantum circuit. Okay, but let's take one step back once more. The aim of this algorithm is again the same as in the classical case. We want to train the parameters of the Hamiltonian such that our sampling probability represents a probability distribution which is given to us through some training data and/or labels. Now for the loss function definition, we in principle have two different possibilities. Either we define a classical loss function. What this means is that we have our quantum state, our quantum Gibbs state, but then we measure from it to get the sampling probability, And then we use this sampling probability to define a loss function. Okay, or we define a quantum loss function. In this quantum loss function case, what we would do is to map our classical probabilities to a rank 1 quantum state, which is then what you see here on the left, this raw data. And then we want to match the full Gibbs state to the state that is defined by this rank 1 quantum state. Now, in the latter case, you have more degrees of freedom that are matched to your probability distribution. But it also differs what you want. So if you only really want to match the classical distributions and avoid to train unnecessary degrees of freedom, then it is sufficient to investigate the first loss function, and this is what we're doing here in this study. Okay, let's talk about our preparation of the Gibbs state. What we are using here is quantum imaginary time evolution. More explicitly, its variational counterpart, which we're going to call var-kite. Kite requires, or kite is defined with respect to an n-qubit Hamiltonian, which is given as a weighted sum of Pauli operators. Now, with respect to this Hamiltonian, we can have a look at the Wick-rotated Schrödinger equation, which defines a normalized version of imaginary time evolution. So if we solve for this equation, we get a form for a time-dependent state that depends on your Hamiltonian, your time, and your initial state phi 0. Now, probably many of you know real-time evolution, and this looks somewhat similar. But what you should notice is that there is an I missing up here in the operator. This missing I leads to the fact that we are not looking at a unitary operator, and this is also the reason why we have an additional normalization factor in here, which ensures that our quantum state is L2 normalized at every point in time. Okay, but how can we now integrate this into a parametrized quantum circuit? What we're doing is we're choosing an input state as well as a parametrized ansatz, which is applied to this input state. And then we use a variational principle, which helps us to translate our state evolution into an approximate parameter evolution. And we'll have a look at this in more depth on the next slide. So, in order to do parameter evolution, we make use of McLaughlin's variational principle. McLaughlin's variational principle basically tries to minimize the difference between the left and the right-hand side of the Wick-rotated Schrödinger equation given a variational subspace. So our state that is given through an ansatz. Now, if we solve for this equation here, we get out a system of linear equations, namely the one down here. Solving for this system of linear equations now gives us a time derivative of our ansatz parameters omega. This, in turn, can be seen as an ODE, which we can use to propagate our ansatz parameters with an arbitrary ODE solver such as explicit Euler, and thereby propagating the parameters according to McLaughlin's variational principle helps us to simulate the state evolution with a constant architecture quantum circuit. Now, to mention, the right-hand side of the system of linear equations is actually proportional to the energy gradient of our system, and the left side is proportional to the Fubini study metric, a metric that describes the information geometry of our answers. Now, the evaluation of A respectively C is quadratically expansive in the number of parameters in our ansatz and linear in the number of parameters in our Hamiltonian. And how can we evaluate them? We can make use of a very nice circuit structure that was actually already come up in 2002, as you can see in the reference at the bottom. What the circuit structure that you see here does is to compute this term here by making use of one additional qubit, some controlled operations, and one measurement. Now, this is a lot to take in. You can check out the paper and think it through. But what I just would like to show you here now is that we can rewrite our items for Aij and Ci in a similar, or actually in this form that you see up here. So we can just use the circuit structure to evaluate all the components that we need for our system of linear equations, defining the ODE for our evolution. Okay, now how does this help us to generate a Gibbs state? Well, maybe you've already seen some similarities in the layout of our states, but let's look at this a bit more closely. The target state that we want looks as follows. What we do now is that we set our time according to the system temperature that we have here. We extend our target Hamiltonian, HA, by an additional trivially acting Hamiltonian on a subsystem B. This subsystem B has the same size as the target system A, and our initial state is now given as n Bell pairs, where one part of the pair always lies in A and one in B. If we now trace out our system B, then what we get is that the initial state on subsystem A is given as a maximally mixed state. Now we use Wahrheit to propagate our state, and we get a state that is propagated by our HAB. If we now trace out subsystem B, what we get is an approximation to our Gibbs state. And to verify that this works, we looked at some simple example, even on an actual quantum computer. So here you see two Hamiltonians, one with 1 qubit and one with 2 qubits down here. Now these Hamiltonians correspond to the Gibbs states that you see here, and we used the Ansätze that are showing to the right to evaluate an approximation to those Gibbs states. Now the task that we wanted to look at is to see how close our approximations are to the actual evolution, to the actual Gibbs state. With each time step, how close do we get, and evaluate this with the fidelity, which is a measure in the closeness of our quantum states. Okay, and now here you see on the left-hand side the training for our H1 for the smaller Hamiltonian, and on the right-hand side for the H2. You see here the fidelity evolution of an exact simulation in dark blue, and for a test on actual quantum hardware, namely the IBM Q Johannesburg 20-qubit machine in turquoise. Now, as we can see, after we've propagated for time 10, so for our target time, we do achieve a very good fidelity in the small qubit case. So we're even rather close to a fidelity of 1, which would be the maximum. And in the the 2-qubit gate, we achieve a fidelity which is about 59%, which is an interesting and already decent result for this small scale study. Okay, now we know how to prepare a Gibbs state. We said that's the centerpiece. Now the question is still, how do we train our quantum Boltzmann machine? So we've seen the loss function before, right? We've seen this function here, our classical loss function. And we know how to get our classical probabilities, namely by measuring our Gibbs state. Now we want to compute the gradient of our loss function to optimize. But this is not so easy. So, in fact, if we have a look at this, we can decompose the subpart up here even further, and this is what you see here. The formulas themselves are not so important. What is important is that the right term in green is easy and efficiently compute. The left term in red can be difficult to compute if certain commutation relations are not sufficed. What this means is in that some previous work that has been done, one would usually not train with the actual gradient of the loss function, but use an upper bound that is given by Golden-Thompson. Now the cool thing about using Varcoid for our QBM is that we can actually make use of the fact that our circuit parameters and their evolution depends on our Hamiltonian parameters. This in turn enables us to evaluate those gradients with automatic differentiation. We can make use of a chain rule. Okay, to just give you a small introduction to the gradients and how difficult it is and what we do, let's have a look at this. So here we see that we have two parts of the gradient. The gradient of the circuit parameters with respect to the Hamiltonian parameters and a gradient with respect to our Gibbs state. The first one is actually simple to compute. This is a first order gradient of a quantum state, which is even implemented in Qiskit. The second term is a bit more difficult because we now need to take the gradient of our system of linear equations that is given by McLaughlin, and for solving the system of linear equations, we need to take some higher order gradients into account. Now, when we compute the system of linear equations, we get the time derivative of this term. What we can do now is to, again, use this as an ODE to actually propagate the gradient of our circuit parameters with respect to the Hamiltonian parameters throughout the Gibbs state preparation. Okay, and just to see where this plugs in, let's have a look at some colors. It's very nice. Now we have those terms and we can actually train the loss function with the true gradient. Okay, now those were loads of pieces. Let's plug them together and take a step back again. The first step of the algorithm is that we want to initialize a Hamiltonian and a set of initial parameters for the Hamiltonian. Then we use Varcoid to prepare our Gibbs state and get the necessary terms for our ladder automatic differentiation. Now we plug in the terms that we found throughout the Gibbs state preparation. We compute the gradient with respect to our Gibbs state and thus evaluate the gradient of the loss function, which we can now use to update our Hamiltonian parameters. Now this routine is being done until we've reached a termination criteria and hopefully learned a good model. Let's have a look at one example. The goal of this training is to learn the sampling probabilities of a Bell state. which is what you see here. The model that we use is a very simple one. We take a diagonal Hamiltonian with 3 parameters in them, and the ansatz is what you see down here. This is what we call an efficient SU2 ansatz in the Qiskit circuit library. One specific property of this ansatz is that it can represent complex phases. Okay, let's have a look at some training outcomes. So, we do choose an initialization for our parameters alpha, beta, and gamma in a uniform distribution between -1 and 1. We use Varkite to prepare the Gibbs state. To do so, we do 10 different steps. Then we get our loss function gradient. We plug the gradient into our optimization routine, which in this case was ARM-SCRUD, and then we train the model. And on the right-hand side, you now see the loss function over the training iterations, as well as the L1 norm, so a distance norm between the target and the trained probability distribution. What you do see here is a standard deviation bar additionally to the single plots, which comes from the fact that we trained this model for 10 different random seeds, and then we averaged over all of them, and as we can see, they all go into similar directions, and the standard deviations get smaller with time. On the left-hand side, we see a bar plot to illustrate this example. The blue bars represent our target, the Bell state sampling probability, and the purple ones, the worst trained example, and the pink ones, the best trained example. And as we can see, the pink ones are already very, very good. So, to sum this now up, what we can do with variational quantum Boltzmann machines is to explore the data structure already, to construct a suitable Hamiltonian, and to have a more targeted state learning. We can, in this case, use automatic differentiation for the quantum Boltzmann machine training, which is inherently coming from the fact that we use Varkite for Gibbs state preparation. And this state preparation learning technique is actually compatible with near-term quantum computers, since we have a constant depth, constant architecture quantum circuit. So, to sum the key messages up of this whole talk again, what I wanted to tell you is that we want to explore quantum algorithms for data processing, and there is some potential there. But in order to explore this, we need to load data into a quantum state. This data loading is potentially difficult. But what we can do is to investigate some approximate but efficient data loading techniques which make use of some quantum machine learning to still be able to investigate the potential of quantum algorithms in this realm and get a better understanding of quantum computers overall. With that, I would like to thank you for your attention, and please feel free to ask any questions.